Okay, so we're talking today about, we're moving into Unit 3.4 here, and we want to start talking about vectors in terms of, we want to develop an algebraic way of representing vectors here. So when we thought about vectors geometrically, we thought of them as these arrows here, where it started at one point, went to another point. So if this went from the point A to the point V, B, we called this the vector AB. Okay? And we said that the length of this arrow represented the magnitude of the vector, and the direction that this arrow pointed told us the information that we needed about the direction of this vector, because a vector has both magnitude and direction. In this unit, we want to start thinking of these things algebraically. So what we can do is we can take this picture we have of a geometric vector, and we can imagine taking this arrow with a tip and a tail and moving it onto our Cartesian plane that we have over here on the right. So if I take my geometric vector and I put it over here, and I put the tail of my vector right on the origin of my coordinate system, I can see that the tip of that vector falls at the point 3, 4. Now, if I think of this in terms of, to specify a vector AB over here, I had to specify the starting point and the ending point. So my starting point now is the point 0, 0. My ending point at the tip of my vector is now the point 3, 4. So if we sort of adopt the convention that we're always going to have our vector start at 0, 0, the only information we have to specify a vector is where the tip of this vector is going to be, where it's going to end. So we could say that this vector AB can be represented by the ordered pair, 3, 4. Okay. Starts at 0, 0, goes to the point 3, 4. And that tells us both the length of it, how long the line is, and what direction it's pointing. So it goes from, say, 0, 0 to this point, 3, 4. Okay. So we'll just say this again down here. Vector AB is equal to, express it in terms of this ordered pair, 3, 4. Now, we might want to talk about the magnitude and the direction of this vector AB separately. Well, how can we find the magnitude of this thing? Well, if we look at our diagram, we notice that, and if you think back to the discussion about components, this vector AB is made up of a horizontal component and a vertical component. We can figure out the magnitudes of these things. I mean, the magnitude of the vertical component is clearly 4. The magnitude of the horizontal component is clearly 3. There's a right angle in there. So we can find the magnitude of the vector simply by using Pythagorean theorem. The magnitude of AB is going to be 3 squared plus 4 squared, and then we take the square root. Okay, so the magnitude of AB is going to be, we work that out, we get 5. So you use Pythagorean theorem to figure out the magnitude. If we want to specify the direction, we're going to need to use an angle, just like it says right there. Well, a convenient angle to use is the angle from our vector to the positive x-axis, that angle theta in there. And again, we can use simple trigonometry to figure out what that angle is. The tan of angle theta is going to be opposite over adjacent, so that's 4 over 3. And so we can work out that this angle theta is going to be 53.13 degrees. And we should also specify what that angle is measured relative to. So this is 53.13 degrees from the positive x-axis. Okay? So we can represent the vector as an ordered pair, and from that ordered pair, that values of 3 and 4, using Pythagorean theorem and the tangent ratio, we can separate this out into magnitude and direction. Now, there's another notation that we're going to use as well. Okay? And this is even more closely related to this whole concept of components of vectors. If I've got my vector again here, we'll call this vector, we'll call it v now, and again it still ends at this point, 3, 4. I can think of it as being made up, again, as a x component and a y component. Okay? And in terms of these two components, we know what the magnitudes are. Our components. So the magnitude of our x component was 3. The magnitude of the y component was 4. We also want a way of specifying the direction of these two components. Okay. Because we don't know whether these are pointing positive direction, negative direction, and we also want to identify which number represents our x component, which one represents our y component. And we said back in Unit 1, 2, that if we wanted to talk just about the direction of a vector, what we could use are unit vectors, because unit vectors had magnitude 1, and they had some special direction. So if we want to just specify the direction that one of these things are pointing, we're going to use unit vectors. So what we're going to define are 2 unit vectors. One unit vector is going to point in the direction of the positive x-axis. So if I just sketch a little xy plane in here, okay, we're going to have one vector. It's a unit vector, so magnitude 1. It points in the direction of the x-axis. And then we're going to have another vector that points in the direction of the positive y-axis, just like that. And we're going to give these names. We're going to call the one that points in the direction of the positive x-axis I hat, okay? The hat meaning that it's a unit vector. And the one that points in the positive direction of the positive y-axis, we're going to call j hat. So that would make over here this one I hat and this one j hat. So this vector 3, 4 that we were expressing as an ordered pair, we'd also given it the name v. We can say that v is equivalent to, well, the sum of these two components, x and y. X is magnitude 3, and it points in the positive x direction, so it's 3 times this I hat vector. And our y component had a magnitude of 4, and it pointed in the positive y direction, so it's 4 times that j hat component. Okay. So this vector v is made up of a sum of these two components, a vector of magnitude 3 in the x direction, positive x direction, and added to it a vector of magnitude 4 in the positive j direction. Okay. So let's just try a couple of examples here. Express the vector shown as an ordered pair and in unit vector notation, and find its magnitude. So we've got a vector here. Let's call this vector v, and let's express it both as an ordered pair and in unit vector notation. What is this going to be as an ordered pair? Richard? How did you know that? Yeah. So we can say that vector v is -5, 6. Okay? Because that's the coordinates of that point that is at the tip of the vector. Or if we wanted to write it in this, using these unit vectors I and j, okay, how can we write it in that ij notation? Yeah. -5 I hat, because we're going in the opposite direction, so we're going in the negative x direction, 5 units, and then we're adding to it a vector that goes 6 units in the j hat direction. Now, how could we find the magnitude of this vector v? How would we do that? Yeah. And we're using Pythagorean theorem. And just to make it absolutely clear, I'm just going to take these numbers here and here, and I'm going to put them straight in. So negative 5 squared plus 6 squared. And we work all this out, and this is the square root of 61. And we can just leave it like that. What if I had another vector that, let's draw this in, and we'll make it green here, just for something to do. I don't know exactly how it goes. We'll just draw it in there like that. We'll call this vector u. We'll say that we know that the magnitude of u is 10, and we know the angle that it makes with the positive x-axis is 40 degrees. Okay. How could we do the same thing for u that we did for v? Okay, write it in that ordered pair notation and in this ij notation. What are we going to need to find for vector u before we can do that? Yeah, so we've got to find the components of u. So for vector u, we'll just say vector u here. We'll find our x component, and we'll find our y component. And what we really need are the magnitudes of these two things. So how do we find the magnitude of the x component? Okay. Yeah. So the magnitude of u times cosine of that angle. So magnitude of u cos 40 degrees. Magnitude of u is 10 cos 40 degrees. And we work that out, and we end up with 7.66. What about for our y component? Exactly. The magnitude of u sine 40 degrees. So 10 sine 40 degrees. And we work this out, and we get 6.43. So we've got the magnitudes of our x component and our y component. How do we put this together to get our vector in ordered pair notation? Okay, so we're going with the ij notation first. All right, 7.66 I hat plus 43 j hat. Yeah, we just put those two magnitudes that we have in there, and we add on our unit vectors to make them to specify the directions. And if we wanted to express this as an ordered pair, what would that look like? Exactly. Okay. So the big advantages of this notation, one that we're going to see is it's going to make all of our calculations easier. The other one is that it can be easily extended to 3 dimensions. Okay. So here, I've drawn myself a 3-dimensional coordinate axis. I've got x, y, and z. And where I see these labels x, y, and z, that tells us which direction is positive. So this arrow here points in the direction of the positive x. Over here we have the positive y direction, and going up we have the positive z direction. Now these x, y, and z axes are all perpendicular to each other. So it's easy to see that y and z are perpendicular. To imagine x being perpendicular, I mean this is 3 dimensions, so this has to be coming straight out of the board here, right towards you guys. So again, it's perpendicular to both the y and the z axis. So what we might be given here is a point or a vector, something like 3, 4, 2. Okay? What does this mean? Well, here we've got it in the coordinate system. So that, again, this could represent either this point here, or it could represent a three-dimensional vector that ends at that point. So we could call this our vector v here. Okay. If we want to go from this ordered pair notation, okay, x coordinate, y coordinate, z coordinate. So our x coordinate here is 3. Our y coordinate is 4. Our z coordinate is 2. Okay, so this is x, y, z. Okay. We can also specify this in terms of these unit vectors that we used before. But instead of just having 2 unit vectors, now we're going to need 3 unit vectors. We're going to have our I hat vector, which points along, I'll just say, points along the positive x-axis. Okay, or is the vector 1, 0, 0. Okay, we've got our j vector, which again points in the positive y-axis direction, or the 0, 1, 0 direction, if we put it into ordered pairs. We need a third vector that points in the positive z direction. What do you think we're going to call that unit vector? And if it's a unit vector, we need k hat. Yep. So it goes in the direction 0, 0, 1. So this vector v that I've drawn here, we could rewrite as 3i hat plus 4j hat plus 2k hat. Okay. That would be in the unit vector notation. We might want to find the magnitude of this vector v. And this is similar to doing it in 2 dimensions. We're going to take each of our magnitudes here, square them, and then take the square root. So it's kind of like the Pythagorean theorem extended to 3 dimensions. So our magnitude is going to be root 29. Okay. Now, in terms of the directions, the way you specify the directions are by what are called the direction cosines, which give you the angle from the vector to each of the x, y, and z axes. We don't have to cover that in this course because we're trying to get away with working with the angles into just working with the algebraic notation. So we don't need to worry about that. They talk about it in the text, but you don't need to worry about it. Okay? So the kind of thing you will be asked to do is something like this. You're given a point for -3, -2, or the vector to the point, or the vector, this could represent a vector, for -3, -2, and you're asked to plot this thing in 3 dimensions. So if we're going to plot it, we should draw ourselves some coordinate axes. Here's how I'd recommend setting up your axes. I would put the y-axis horizontally with the positive y direction going towards the right. I would put the z-axis vertically with positive going up. And your x-axis is going to be the one that is coming straight out of the board. So we sort of draw this at a 45-degree angle here to give the illusion of something coming out of the board here. Okay. Now, if we want to plot this thing, they're giving us our coordinates here. That 4, our first ordered pair, means we want to go 4 along the positive x direction. So positive x direction is along like this. We can just sort of tick off 1, 2, 3, 4, and sort of put a dot there to remember that that's as far as we had gotten. Next step is our y component. So we want to go 3 in the negative y direction. So if the positive y direction is to the right, we want to go 1, 2, 3 the opposite way. But we want to start from where we left off with our x-axis. So starting from this big dot that I've made here, we'll go over 1, 2, 3, and we'll give ourselves another big dot here for our second little stopping point. Our third step is going to be 2 units along the negative z-axis. So positive z is up, negative z is going down, so we want to go down 1, 2, but again we want to start from where we left off with y. So go down 1, 2, and after we've done x, y, and z, that's our stopping point. So that would be our coordinate for negative 3, negative 2. Okay. And what the textbook does is it kind of fills in the rest of the sides here. So the whole thing looks like a big rectangular prism. Okay. Where 0, 0, 0 is at one corner of it, and the point that you're going towards is at the far coordinate. So if we were to draw on the vector, we would just make ourselves a line starting at the origin, ending at that point that we have just plotted. Okay. And there's our vector.